Hey there everybody, we're getting close to wrapping up this module in chapter 8. We just have to get through lesson 8.4 for the next 2 days, and then we'll be prepping for a test on this module. So this was another short one, and we're going to finish up with a discussion of improper integrals and what those are and how to properly evaluate them. Improper integrals are defined in two ways, both horizontally and vertically. So today we'll tackle horizontally, we'll save vertically for tomorrow. So let's define what an improper integral is. An indefinite integral, which is something that we've learned last year and this year, is an integral that's evaluated without bounds. And so without bounds, all you can do is come up with an antiderivative plus c, and then that's the end of that. A definite integral is something that has specific bounds from a to b. And so when you evaluate that with an antiderivative, you can come up with a specific definite answer, a numerical answer which represents the area between bound A and bound B. So an improper integral is a definite or partially definite integral where one of the bounds is infinite. So one example is an integral that goes from a to infinity. So how do you find the representative area if it never stops, if it just keeps going? Is it possible to find the value of an area if the bound is infinite? Or you can have a lower bound be negative infinity and an upper bound be finite. So again, coming from the left side, is it possible if that doesn't have an endpoint? Is it possible to evaluate that? And then finally, what if both of the bounds are infinite? Is it possible to find the area under a curve where neither endpoint exists? And it might blow your mind to find this out, but the answer is yes. So we're going to tackle that today, how to evaluate not every improper integral, but many improper integrals can be evaluated. Well, the only way that we can tackle that is using limits. Right? We cannot evaluate something at infinity, but we can approach infinity. So in our different cases, if you've got a lower bound of a with an upper bound in infinity, then you're going to replace the upper bound with b and then precede it with a limit as b approaches infinity. Similarly, if you have a lower bound of infinity, you will replace your lower bound with a and then have your limit as a approaches infinity. And if you have both negative infinity to positive infinity, you will need to pick an arbitrary c value at which the function is defined, and you need to separate the integrals into something where c is the upper bound of one and c is the lower bound of the other. And then once you've done that, then you'll also include limits. So then I would have a limit where a goes to this arbitrary c and a approaches negative infinity of f of x. And then I'll introduce another second limit, and my bounds will go from c to b, and b approaches positive infinity of f of x dx. So we're going to use the combination of the first and second rules along with an arbitrary split of the interval at a value c. So let's put this into actual practice. How will we know? We're going to use these words of converge and diverge. So an improper integral will converge if the evaluation of the limit gives me a constant value. 0 is okay in this case. It doesn't have to be something other than 0. 0 is considered a constant, so then we say it converges. But we will say the improper integral will diverge if the limit does not approach a constant. If the limit is still undefined as plus or minus infinity, then that's a divergent improper integral. So we're going to try and prove one way or the other. Is it convergent or divergent? Remember, convergent means it is approaching but not necessarily reaching that value. Divergent means it doesn't approach any value at all. Okay, let's tackle the integral from 1 to infinity of dx over x. So we recognize that the upper limit is the problem here. So we start out with replacing that upper limit with b. So we'll be going b is approaching positive infinity. And I'm going to write this as 1 over x times dx. So what I'm going to do now is focus on evaluating this integral first, and then I'll apply the limit after I've evaluated it. So the limit as b approaches infinity. The antiderivative is the natural log of the absolute value of x plus the constant c going on the interval from 1 to b. The limit as b approaches infinity would be the natural log of the absolute value of b plus c minus the natural log of the absolute value of 1 minus c. Now we know that the natural log of 1 is 0 and that the c's will cancel each other out. And so now I can apply the limit and I will have the natural log of the absolute value of infinity, which is infinity. And so we conclude that this is a divergent integral whose area does not approach any particular value. All right, let's look at the integral from negative infinity to positive infinity of the exponential function e to the x. So we'll have to replace both bounds here, and we're going to pick an arbitrary value that's defined. I could pick 0, 1, it really doesn't matter. I'll just pick 0 because it's right in the middle. So I am going to split this up into an integral going from a to 0 of e to the x dx. And I'm also going to split it up then from 0 to b, e to the x dx. And then my limit, a should approach negative infinity, and b should approach positive infinity. And so I evaluate these antiderivatives. Antiderivative e to the x is e to the x plus c, evaluated from a to 0. And then the limit of, again, the same antiderivative, evaluated from 0 to b. So we now have one limit as a approaches negative infinity of e to the 0 plus c minus e to the a minus c. And then a second limit of e to the b plus c minus e to the 0 minus c. All right, so we know our plus c minus c's cancel each other out. Also going to cancel each other out. E to the 0 is 1 here, minus e to the 0 here. And so we are left with e to the negative infinity plus e to the positive infinity. So 1 over e to the infinity plus e to the infinity, which is 0 plus infinity, which is divergent again. All right, now just so you don't think that every integral turns out divergent, let's do one that doesn't. Okay, here we go. We have another integral with two differing bounds, two improper bounds. So I'm going to split this, and again, just to show you, it doesn't matter, I'll split this one at 1. So I'm going to set up my integrals to go from a to 1 of 2 over 1 plus x squared dx, and then a second integral going from 1 to b of 2 over 1 plus x squared dx, where the limit as a approaches negative infinity and the limit as b approaches positive infinity. Now the antiderivative of 2 over 1 plus x squared is an inverse tangent. So I have 2 times the inverse tangent of x plus the constant c going from a to 1. And then, whoops, b approaches infinity. 2 inverse tangent of x plus c going from 1 to b. All right, let's evaluate that and see what we come up with. So we have 2 times the inverse tangent of 1 plus c minus 2 times the inverse tangent of a minus c. And then plus my second limit, two times the inverse tangent of b plus c minus 2 times the inverse tangent of 1 minus c. Get that all in the same window here. All right, so we can clean this up. We also have 2 tangent inverse of 1 minus 2 tangent inverse of 1. So we're left with negative 2 times the tangent inverse of negative infinity plus 2 times the tangent inverse of positive infinity. Now, inverse tangent of negative infinity is an x value that produces that. Think about your where the asymptotes happen for tangent. So this would be negative 2 times negative pi halves. And then we've got 2 times, and that asymptote happens at pi halves. So this ends up to be pi plus pi, which is 2 pi. So this is a convergent improper integral. And if we think geometrically about that, that means that the area trapped under this particular curve approaches 2 pi. It might not actually reach 2 pi, but it will converge to a value so close to 2 pi, and it will never exceed that value. So we call this a convergent interval. Okay, let's try another one. Here we have just a single bound that's improper, so we only need to replace the upper value of 0. So the limit as b approaches infinity of 2 over, and you might recognize this as factorable, x plus 1 and x plus 4. Now, in order for me to be able to integrate this, we're going to have to do a little work on partial fractions. So we'd have to, zoom over here to the side and set up an x plus 3 and an x plus 1, and that needs to come out to be equal to 2 times x plus 3 times x plus 1. So I'm not going to talk down to you today and help you remember how to do that. Let's just assume that we have done all of the work for the partial fractions, and that a turns out to be -1 and b turns out to be +1. All right, so let's go back to the task at hand. So we're integrating, whoops, what did I do? No, I just looked back. Let me clean this up here a second. Erase. We have the right, you probably are caught me in that already. I wrote it right on the other side over here. Did I write these correct here? Yeah, okay. So negative 1 over x plus 3 and positive 1 over x plus 1 dx. All right, so our antiderivatives here. The negative natural log of the absolute value of x plus 3 plus the positive natural log of the quantity x plus 1 plus c evaluated from 0 to b. Okay, now I want to caution you, don't jump into plugging in infinity before you've plugged in your bounds. Okay, so hold off on evaluating the limit. Sometimes people get a little eager. So we want the negative natural log of the absolute value of b plus 3 plus the natural log of the absolute value of b plus 1 minus, plus the natural log of 3 and then minus the natural log of 1. All right, so we know that the natural log of 1 is 0. We also know that we can take these logarithms right here, and we can use some of our log properties to write that as a quotient instead. So I'm going to slide over. So I'll have the limit as b approaches infinity, and I'm going to put that together as a single, b plus 1 in the numerator and b plus 3 in the denominator. And then I've got plus the natural log of 3 as a constant. Now if I plug infinity directly in right now, I'm going to get infinity over infinity, infinity plus 1 over infinity plus 3, which doesn't really do me any good. So you have to remember our rules for how, before we plug infinity in, to divide through by the highest power. Okay? So the highest power is to divide everything through by b. So we want to do that first before we plug in. So let's get rid of, we're not ready to plug in quite yet. Okay, and we're going to divide. Okay, so the limit as b approaches infinity, we'll have the natural log of 1 plus 1 over b over 1 plus 3 over b, and then plus the natural log of 3. Okay, now you can plug your infinity in. So we'll plug in infinity here and here, which is going to give me 0 in both cases. So I end up with the natural log of 1 plus the natural log of 3. And we know the natural log of 1 is 0. So the answer is the natural log of 3. Sorry, I'm totally running out of space here, which is convergent. Yay. I should have planned out my work. All right, so now we are ready to tackle something. We got a little bit of everything going on here. We're going to end up using L'Hopital's, but before we do that, this is a product, and so our good friend integration by parts is going to need to come into play here too. So we're going to see a lot of interesting stuff going on in this question. So first, let's replace the bounds. So I want to go from 1 to b approaching infinity, so e to the negative x dx. All right, as a product, we need to set up our integration by parts, and we use our Lipit test. So that polynomial x is going to beat out the e to the negative x dx. So I'll have dx as my derivative and negative e to the negative x as my antiderivative. All right, so integration by parts gets me to the following. We'll go this way. So negative x e to the negative x minus the integral of negative e to the negative x dx. And so let's just take care of that and have plus, and our bounds are 1 to b. And then we can simplify that by evaluating the integral. So negative x e to the negative x minus e to the negative x as the antiderivative of the second integral, going from 1 to b. Okay, again, don't put your infinity in until after you've put your b in as your bounds. All right, so negative b e to the negative b minus e to the negative b plus c. Okay, now let's drop in 1, so plus e to the negative 1 and plus, so double negative, another e to the negative 1 minus c. All right, what do we have all together now here? The limit as b approaches infinity of negative b over e to the b minus 1 over e to the b plus 1 over e plus another 1 over e. Okay, so let's look at these kind of piece by piece. Negative b over e to the b. And then let's apply the limit of negative 1 over e to the b. And then 1 over e and 1 over is a constant. And so if I add those together, I'll have 2 over e. They've got a common denominator, so I can add them together. All right, let's evaluate. We'll plug in infinity. We have infinity over infinity. That's an indeterminate form. If I plug infinity in here, I'm going to have negative 1 over infinity, so that would be 0. So the only one I need L'Hopital for is this first one. And so L'Hopital tells me negative 1 over e to the b. And then I've got plus negative 1 over infinity, which is 0. And then I have 2 over e, which is a constant. So now I'm ready to plug infinity in here, which is going to give me negative 1 over infinity again. So all together, I end up with negative 1 over infinity plus another negative 1 over infinity plus 2 over e. Both of these go to 0. So I end up with 2 over e as a convergent value to the improper integral. So again, it's just kind of like if I look at the area trapped under the function e to the times e to the negative x, x times e to the negative x, starting at 1 and going all the way out to infinity, that area will converge to the value of 2 over e. It has a finite answer. An infinite integral has a finite answer. It really just kind of blows my mind.